So in our demonstration, we incorporated conservation of energy, momentum, and kinematics. Basically what we have here is a pendulum, and we have the pendulum, we raise it up to a height so it's horizontal with its pivot, and then we release it from rest. And the pendulum goes down and hits this other ball, and this ball has identical mass, and it's also made of the same material, which is metal. And that this ball right here, it comes to rest, and all of its kinetic energy is transferred to this ball, and this ball comes flying off the table. This ball is moving in 2D motion, so in the y direction it's initially at rest, and then in the x direction it has all of the kinetic energy that this ball has from the conversion to potential energy to kinetic energy. And this ball, it goes down and goes in the cup, and using all of three of these principles we can calculate the distance that it will travel, so we know where to put the cup so that this ball will land in that cup. So here we have the setup that we try to illustrate on the board, and we have a pendulum here. It's hung by 2 strings onto this stand on the table, and we have the ball here that's currently at rest. And so basically we're going to take this and pull it back so it's horizontal with the stand and drop it, and it's going to hit this ball, and this ball is going to fall on the floor, and the cup is approximately 1 meter away from the edge of the table. And if our calculations are correct, it should land in the cup.
For this problem, first we need to use the conservation of energy, which is kinetic energy initial plus the potential energy initial is equals to the kinetic energy final plus the potential energy final. So this is the initial position, and this is the final position. When it's at the initial position, the kinetic energy is 0. And the potential energy is mgh. When it's at this position, the final kinetic energy is 1/2 mv squared. And the potential final energy is mgh. Since h at this point is equals to 0, so that becomes 0. So what we have is mgh is equals to 1/2 mv squared. Since they are identical, the m's cancel out. And v is equals to the square root of 2gh. So let's plug in the numbers. V is equals to 2 times 9.8 and times the height here, which is 0.37 meters. And V is equals to 2.693 meters per second. Let me write this down. The V here is equals to 2.693 meters per second.
We have a ball that is of the same mass and material at the edge of the table, which is at rest. This ball will hit this ball, and this ball will come flying off the table as a result. So if we break that down into steps, we have this ball that is approaching this ball with the speed of v, and they hit each other. When you have a collision, you write the momentum of collision. And basically, this is a collision where momentum is conserved. So the momentum initial of the system is equal to the final momentum. And so this ball hits this ball, and so the full equation for momentum that's the full equation for momentum, because momentum equals mass times change in v. So first, let's just call this ball 1 and the other ball 2. This ball has a mass of whatever, and it has a speed of v1 initial, which is the v that we got from here because it fell from that height. But this ball has a mass of 2 initial, but its v is 0 because it's initially at rest. So this cancels out. So when we have the collision like this, the type of collision this is a perfectly elastic collision. So because these balls have the same mass, all of the kinetic energy that this ball has will be transferred to this ball. So the first ball that fell down will have V of 0, and this ball will come flying off the table with the same velocity that this ball had. So that makes M1 initial, V1 initial equals M2 initial, V2 final. So since they have the same mass, these m's cancel out, and so we have V1 initial equals V2 final. So basically V2 final is also equal to 2.693 meters per
For
second.
part 3, we're using the kinematic equations. Since the ball fall off the table is a projectile motion, in order to find this distance, the range here, you can use the equation change in x is equals to v horizontal times time. And now we need to find the time. So change in h, which is the top from the top of the table to the top of the cup, is equals to v(y naught t) plus 1/2 at squared. And v(y naught) is the speed when the ball's here at this position, which is 0. So that goes to 0. And the change in h, as I said, is from here to here. So which is the h of the table minus the h of the cup is equals to 1/2 at squared. And let's plug in the numbers. The h of the table, the height of the table, is 0.915 meters. And the height of the cup is 0.13 meters. It's equals to 1/2 9.8 times t squared. And we got t is equals to 1.078 meters. I mean seconds. Oh no, wrong. It's 0.47. Change in x is equals to v horizontal, which is we calculate here is 2.693 meters per second times the t, 0.4 meters. And we got the change in distance, change in x is equals to 1.078 meters. So, let's do the experiment.
Yeah, dude, I just walk down the street, dude. Bye-bye.
So much smoother. It would have been so much more smoother.
This class, if I didn't have this class, like I read the book,
I never really studied my
As you can see, the ball did not actually land in the cup. This is because previously we said that the collision that occurred was a perfectly elastic collision. And that's not actually the case, because a perfectly elastic collision is actually very hard to do, because in a collision there's usually energy that is converted to heat and sound, and when energy is converted to these forms, it's usually very hard to get back. So when you see these balls colliding, you can hear them making a sound. That's where the energy is coming from, and even though there's a lot of kinetic energy transferred, not all of it is transferred because the energy is being converted to those forms.
we have to turn it in.
Yeah, you should do it.
Oh, shit, those are actually pretty decent.
I can't find it. Okay, stop.